oddity lies in the different criteria used for sizing equipment grounding conductors, or EGCs, within the National Electrical Code, or NEC. Specifically, Table 310.16 and Table 250.122 base the EGC ampacity on the overcurrent device protecting the circuit. However, Article 250.122b dictates that the EGC size be based on the size of the ungrounded conductors. This discrepancy leads to situations where a larger breaker might be permissible with a smaller EGC. Let's delve into the details. Table 310.16, allowable ampacities of insulated conductors rated up to and including 2000 volts, provides the ampacity ratings for various conductor sizes based on their insulation type and installation conditions. When selecting a conductor, it must have an ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. This ensures the conductor can safely carry the intended current. Table 250.122, minimum size of equipment grounding conductors for grounding raceway and equipment, specifies the minimum size of the EGC based on the rating of the overcurrent protective device in the circuit ahead of the equipment. This table links the breaker or fuse size to the required EGC size, ensuring a low impedance ground fault path. Article 250.122b, increased size where ungrounded conductors are increased in size, addresses situations where the ungrounded conductors are increased in size to compensate for voltage drop, as required by 215.2a on for feeders and 310.15 done for branch circuits. In these cases, the EGC must also be proportionally increased in size. Let's consider an example. Suppose a subpanel in a detached garage is fed from a 2-pole 20-amp breaker in the main panel. The electrician has replaced it with a 2-pole 30-amp breaker. Assuming number 10 American wire gauge conductors are used, it's crucial to verify their ampacity rating based on Table 310.16. If a 50-amp breaker is considered for the subpanel, a number 8 American wire gauge conductor would be sufficient based on its ampacity. Referring to Table 250.122, a number 10 American wire gauge EGC would initially seem adequate for a 50-amp overcurrent device. However, if the feeder run is long, say 100 feet or more, voltage drop becomes a concern. To mitigate voltage drop, the conductors might be upsized to number 6 American wire gauge. In this scenario, Article 250.122b comes into play. Since the ungrounded conductors are increased to number 6 American wire gauge, the EGC must also be increased proportionally. This means the EGC would need to be upsized from number 10 American wire gauge to number 8 American wire gauge. Now, what if a 60-amp breaker is used instead? The number 6 American wire gauge conductors would still be required to handle the current and voltage drop. However, according to Table 250.122, a number 10 American wire gauge EGC would be sufficient for a 60-amp overcurrent device. This highlights the seeming contradiction where a larger breaker allows for a smaller EGC. The key to understanding this lies in recognizing the different criteria at play. Table 250.122 bases the EGC size solely on the overcurrent device rating, while Article 250.122b considers the size of the ungrounded conductors. When the ungrounded conductors are upsized for voltage drop, Article 250.122b mandates a corresponding increase in the EGC size, irrespective of the overcurrent device rating. In essence, if the conductors are upsized, the EGC also needs to be upsized to maintain a safe and effective ground fault path. The initial selection of the EGC size is still governed by Table 250.122 based on the overcurrent protection device rating. Upsizing is only required if the ungrounded conductors are increased in size due to voltage drop considerations. It's crucial to consult the NEC in relevant tables and articles to ensure proper EGC sizing in any electrical installation. The goal is to provide a low impedance path for fault currents to safely return to the source, facilitating the rapid operation of the overcurrent protective device and minimizing the risk of electrical shock. When calculating voltage drop, you can use the formula voltage drop equals 2 times the length in feet times the current in ounce times the impedance per foot divided by 1000. The impedance per foot can be found in NEC Chapter 9, Table 9. The maximum voltage drop for feeders and branch circuits is 3% and 5% respectively. In the initial scenario, with the 20 amp breaker replaced by a 30 amp breaker, it's important to evaluate if the number 10 American wire gauge conductors are appropriately sized for the increased current. Number 10 American wire gauge copper conductors with type THHN insulation, for example, are typically rated for 30 amps in accordance with Table 310.16, assuming the ambient temperature is 30 degrees Celsius or 86 degrees Fahrenheit, and there are no more than 3 current-carrying conductors in the raceway. However, other factors can affect the ampacity. Temperature correction factors from Table 310.15 must be applied if the ambient temperature is higher than 30 degrees Celsius. Adjustment factors from Table 310.15 must also be applied if there are more than 3 current-carrying conductors in the raceway. If the number 10 American wire gauge conductors are determined to be undersized, they must be replaced with conductors of adequate ampacity, such as number 8 American wire gauge, which is typically rated for 40 or 45 amps depending on the insulation type and conditions. The overcurrent protection device should also be sized appropriately for the conductors. NEC 240.4d states that overcurrent protection for conductors must be in accordance with their ampacities, unless otherwise permitted or required in 240.43g. In the case of the subpanel, it should be rated to handle the intended load. If the existing subpanel is rated at 60 amps or more, it may be suitable for a 50 amp or 60 amp breaker. If the subpanel is rated less than 60 amps, it should be replaced with a panel of adequate rating. It is vital to ensure all electrical work complies with the NEC and any local amendments. A qualified electrician should perform the work to ensure safety and proper installation. Electrical installation should be inspected by the local authority having jurisdiction to verify compliance with applicable codes and standards. Proper grounding and bonding are critical to electrical safety. The grounding system provides a low impedance path for fault currents to return to the source, while bonding ensures that all metal parts are at the same potential, minimizing the risk of electrical shock. The grounding electrode system, consisting of items such as ground rods, ground rings, or metal underground water pipes, must be properly installed and connected to the service equipment. Bonding jumpers must be used to connect metal enclosures, raceways, and equipment to the grounding system. A ground fault circuit interrupter, or GFCI, is a safety device that detects ground faults and interrupts the circuit to prevent electrical shock. GFCI protection is required in many locations, such as bathrooms, kitchens, and outdoor areas. The use of arc fault circuit interrupters, or SIs, provides added protection against arc faults, which can cause fires. SIs are required in many branch circuits applying dwelling units. Regular maintenance of electrical systems is essential to ensure safety and reliability. This includes inspecting wiring, connections, and overcurrent protective devices. Any damaged or deteriorated component should be replaced promptly. The electrical panel should be kept clean and free of obstructions. Overloaded circuits should be identified and corrected. Extension cords should be used only temporarily and should not be overloaded. The use of surge protective devices can help protect sensitive electronic equipment from voltage surges caused by lightning or other events. Surge protectors should be installed at the service entrance and at individual equipment locations. The NEC is updated every 3 years to reflect changes in technology and best practices. It is important for electricians and other electrical professionals to stay current with the latest code requirements. Continuing education and training are essential for maintaining competency in the electrical field. Safe work practices are paramount when working with electricity. These include energizing circuits before working on them, using appropriate personal protective equipment, and following lockout-tagout procedures. Always assume that electrical circuits are energized unless they have been verified to be de-energized. Electrical safety is everyone's responsibility. By understanding the principles of electricity and following safe work practices, we can prevent electrical accidents and injuries. In summary, understanding the intricacies of EGC sizing requires careful consideration of Table 310.16, Table 250.122, and Article 250.122b. By adhering to the NEC guidelines and engaging qualified professionals, electrical systems can be installed and maintained safely and effectively. The relationship between conductor size, breaker size, and EGC size is not always intuitive. While Table 250.122 dictates that a larger breaker can, in some instances, be paired with a smaller EGC, Article 250.122b introduces a conditional upsizing requirement based on the ungrounded conductors. Ultimately, ensuring electrical safety and code compliance demands a comprehensive understanding of these interconnected factors. Always consult the latest edition of the NEC and seek guidance from experienced electrical professionals to ensure adherence to the applicable regulations and best practices. Remember, voltage drop calculations are essential for determining the appropriate conductor size to minimize voltage loss over long distances. A formula for voltage drop is voltage drop equals 2 times the length times the current times the resistance per foot for single-phase circuits, or voltage drop equals 1.732 times the length times the current times the resistance per foot for three-phase circuits. The resistance per foot can be found in NEC Chapter 9, Table 8. Conductors must be protected against physical damage. When exposed to physical damage, conductors must be installed in rigid metal conduit, intermediate metal conduit, electrical metallic tubing, or other approved raceways. The type of raceway must be suitable for the environment in which it is installed. Wet locations require watertight or rain-tight raceways and fittings. Corrosive environments require raceways and fittings made of corrosion-resistant materials. The installation of underground wiring requires special attention. Underground conductors must be direct burial rated or installed in underground raceways. Depth of burial must comply with NEC requirements. The underground raceway must be properly supported and protected from damage. Warning tape or other means of identification must be used to indicate the presence of underground wiring. The proper selection and installation of electrical equipment are critical for safety and performance. Electrical equipment must be listed or labeled by a recognized testing laboratory. The equipment must be installed in accordance with the manufacturer's instructions and the NEC. Equipment must be protected from physical damage, moisture, and corrosion. The equipment must be properly grounded and bonded. Electrical inspections play a vital role in ensuring the safety and compliance of electrical installations. Electrical inspectors review plans, inspect installations, and enforce code requirements. Inspections are typically required for new construction, renovations, and repairs. It is important to cooperate with electrical inspectors and address any deficiencies promptly. Electrical safety training is essential for all individuals who work with or around electricity. Training programs should cover topics such as electrical hazards, safe work practices, personal protective equipment, and lockout-tagout procedures. Regular refresher training is necessary to maintain competency. Electrical emergencies can occur at any time. It is important to know how to respond to electrical emergencies, such as electrical shocks, fires, and downed power lines. Call 911 or the local emergency number immediately. Do not approach downed power lines. Turn off the power at the main breaker if it is safe to do so. Provide first aid to victims of electrical shock. Remember, safety first.